Hello, this video will be on acid-base reactions. So reminder, as you are writing reactions, here's where nomenclature becomes important. So now's a good time to go back and review your nomenclature, like your polyatomic ions and things like that, how to name ionic compounds, and also how to name acids, since we are dealing with acids here. So remember, there's three main categories of acids, and you can pause for a minute to look at this slide to review your acid naming rules. Okay, so summary, we're going to be looking at acid-base reactions here. And there's the three different types of acid-base reactions we'll be looking at: strong acid with strong base, weak acid with strong base, or strong acid with weak base. A quick vocabulary thing is the ionic compound that's produced during an acid-base reaction is known as a salt. So salt is not just sodium chloride, it's a broad category that includes lots of ionic compounds. Alright, so we'll see some examples of what those salts are. So let's get into it. Let's look at our first type. This is when you have a strong acid with a strong base. Thing to keep in mind, since they are strong, what that means is they completely dissociate. So they totally turn into ions. So you have to consider your spectator ions when you're writing out your net ionic equation. So for these ones, I'm going to write out the molecular version first and then the net ionic one. So molecular version looks like this. It's where you treat it as if they are actually stuck together as molecules. So hydrochloric acid is HCl, sodium hydroxide is NaOH. You'll notice that this looks like a double displacement reaction. So it's compound plus compound. The hydrogen and the sodium are going to switch places. So now the sodium is paired up with the chloride, and the H is paired with an OH, which makes liquid water. So looking at our states of matter, these were all aqueous, and since our initial things are strong acid, strong base, that means they totally ionize. So HCl is really H plus and Cl minus ions. Sodium hydroxide totally ionizes. Sodium chloride, think about our solubility rules, that's totally soluble, so it's going to ionize. The only thing that doesn't ionize is water. Okay, so then if you go back and look at your spectators, looks like chloride is a spectator, sodium's a spectator. The only thing that's left over that's truly reacting is your hydrogen ions, and your hydroxide ions react to form liquid water. This is the net ionic version of this equation. Here's a prettier version of it over here. Notice the pH of my products is 7. So this is pure neutral water. So when you have a strong acid, strong base, your product is neutral. Let me flip back to this previous page. Another way to think of it is the salt that is formed during a strong acid, strong base reaction is neutral. So we'll notice sodium chloride is a neutral salt. We'll find that not all salts are neutral. And if you think about, why is this salt neutral? Well, the cation is the cation from a strong base, and we said those cations are neutral. And the anion is a conjugate of a strong acid, and the conjugate of a strong acid is neutral. So this is a neutral salt. So at the end I have just water. It's neutral. Okay, so let's look at, we have a weak acid, strong base. So remember, our strong acids totally dissociate. Weak acids do not dissociate. Okay, so let's look at an example down here. Nitrous acid and potassium hydroxide. So nitrous acid is different from nitric. So remember, if we see the us name, that means that it comes from the ite ion. So nitrous comes from the nitrite ion, which is different from nitrate. Nitric acid is a strong acid, nitrous acid is a weak acid. Okay, so let's take a look at the molecular version of this. I've got nitrous acid, that's HNO2, and that's aqueous. Potassium hydroxide, that's aqueous. This is going to be basically a double displacement reaction, so the H and the K are going to switch places. So now the K is with the NO2, and the H is with the OH, which makes water. Okay, now I'm going to ionize whatever needs to be ionized. So HNO2 is going to stay stuck together. Why? Because it's weak. So weak acids mainly stay in the molecular form. They don't ionize very much. And then my KOH is a strong base. It's a aqueous ionic compound, so it will dissociate. My salt right here, KNO2, it's soluble because I know all alkali metal compounds are soluble, so it is going to dissociate. And then my water stays stuck together. So if you look, who's my spectators? It's potassium. I only have one spectator ion. So my overall reaction is I've got my weak acid reacts with a hydroxide ion to make the nitrite ion and liquid water. Okay. Again, over here, here's a prettier version of it. And if we think about what's happening here, so we saw in the previous reaction the product was neutral, and we call it neutralization reaction. But you don't always get a neutral product in this type of reaction. So here, in this case, like if this right here is my weak acid, notice that what's left behind after this reacts is A-, which is the conjugate base of a weak acid. And the conjugate base of a weak acid is itself a weak base. So this solution at the end is going to have a pH of greater than 7. It is going to be a basic solution. Going back to this previous page, the other way to think of it is you could say that this salt is basic. Remember, we spent a bunch of time talking about predicting the pH of salts and what's going on here. So potassium nitrite is a basic salt. That's because the nitrite ion is the conjugate base of a weak acid. So your product here is going to be slightly basic. Okay. And if we have a strong acid with a weak base, remember, strong acids totally dissociate, but the weak base will not. This reaction is going to look a little bit different than our other two examples. So let's write out an example here. So my weak base is ammonia. So ammonia is NH3. And my acid is hydrobromic acid. Okay, that's HBr. What happens here is, notice how there's no hydroxide in my base, so I actually don't make water. That's what makes this type look a little different from the others. So no water is formed. And what happens is the base just is going to take a hydrogen. The molecular form, let's write the molecular form first, which is actually maybe not as intuitive. The molecular form is actually this. NH3 and HBr just combined to make NH4Br. This right here is our salt. Okay, let's look at the net ionic version, which is the kind that you'll typically want to write. So really what's happening is this aqueous ammonia molecule is going to react with the hydrogen ions from my strong acid, making NH4+. So this is my overall reaction. Notice my product here is the conjugate acid of a weak base. So in this case, the products of my neutralization reaction are actually going to be slightly acidic because I have made the conjugate acid. Okay, so again, this reaction looks a little bit different than the other two. But just remember, bases are hydrogen takers. If you think of it that way, then it'll make sense. Yep, it's going to take a hydrogen, and it's going to leave you with conjugate acid. All right, let's look at some examples with you have something that's polyprotic. So in these examples, it depends on how much of the base or acid that you add. Okay, so here's an example. Let's say we're looking at phosphoric acid. So you've got H3PO4 and sodium hydroxide. Phosphoric acid potentially has 3 hydrogens that it could lose. So, but if you read this problem carefully, it says equal volumes of 1 molar phosphoric acid and 1 molar sodium hydroxide are mixed. So that means you're adding equal amounts of hydroxide. You're adding, I should say it this way, you're adding 1 hydroxide for every 1 phosphoric acid. So it might actually make sense to not even write the molecular version and just write it this way. So really, for every 1 H3PO4, you're adding 1 hydroxide. So I only have enough hydroxide to use up 1 of these H's. So I'm going to make 1 H2O, leaving behind H2PO4 with a minus charge. Okay, if I add So this would be my reaction here. I'm only going to use up one of those 3 hydrogens. Here's another scenario. Let's say H3PO4. Let's say I add double the hydroxide. I add 2 hydroxides for every one of these. Then I can make 2 waters and use up 2 of these hydrogens. So in this case, I would leave behind just HPO4 2-. So it depends on how much you add. And if you add a ton of hydroxide, if you had excess hydroxide, I could use up all 3 of my hydrogens. So this is a little bit trickier here. Okay. You could have a similar scenario in which something can be like dibasic. It's kind of like being diprotic, but the opposite. So an example here would be the carbonate ion. So the carbonate ion has a -2 charge, so it potentially could take 2 hydrogens. Okay, so it's going to be similar to what we saw on the previous page. Let's say I have the carbonate ion reacting with hydrobromic acid. If you add equal amounts of these, then what you'll make is HCO3-. So every carbonate will take 1 hydrogen, making the bicarbonate ion. But let's say you're adding extra hydrogens. Let's say you're adding double the concentration, so you have 2 hydrogens for every 1 carbonate. Then my carbonate will take 2 hydrogens and make H2CO3, which is carbonic acid. So either can happen depending on how much of that acid that you add. So I'm going to summarize. In general, these reactions look like double displacement reactions. So acid plus base makes salt plus water. Salt is that other ionic compound that you form in this reaction. Here's a summary of what the reactions look like. If it's strong acid, strong base, the reaction's always the same. It's H plus OH makes H2O. Everything else ends up being a spectator. Okay, if it's a weak acid, strong base, you have whatever your weak acid is plus a hydroxide ion, and you leave behind the conjugate base of your weak acid. If it's strong acid with a weak base, then you have your H plus from your strong acid reacting with your weak base, leaving behind the conjugate acid of that weak base. And this becomes particularly important when we talk about titrations, these 2 things in particular. So you want to think about in a titration, when you hit the end point of the reaction, what is actually in your solution. And it might not really be neutral at the end point. It could be acidic or basic, depending on which salt you are making.